Hello everyone, welcome to lecture 18 on the series Differential Equation and Discrete Mathematics. In this lecture we will discuss the solution to the homogeneous equation with constant coefficient. In fact, the second order linear homogeneous equation with constant coefficient. As we know that solving a second order differential equation is the cumbersome task, we solve its simplest form, that is a linear homogeneous equation with constant coefficient. Now what does this mean? We have a linear equation, that is y double prime plus ay prime plus by is equal to 0. Now constant coefficient is the term we used because of this constant that are appearing. Here we restrict ourselves for that p and q, which was a function of x, to simply a constant which is independent of x. So now we develop the method to solve this kind of differential equation. So basically we first guess the solution for this. Since this is a homogeneous differential equation, we can guess the solution for this very easily. In fact, we have solved, we know, we have seen a method to obtain this analogous homogeneous linear equation with order 1. So that is of the form y dash plus ay equal to 0. We all know that the solution of this is nothing but e raised to minus ax and some constant multiplied to it. So similarly, now since you see that this can be written as this equation 1 can be written as y double dash plus ay prime is equal to minus by. And we see that the derivative is repeating. The derivative, we want that function even after differentiating on the right hand side to occur. So we want this left hand side to satisfy this right hand side. So that means we want this y double prime plus y prime to be equal to minus by, so that y, the function y, is appearing over here once again. So what kind of function would work in this situation? So obviously we look for a function which is almost similar to this form. So that is a solution, a function of the form e raised to mx. So we consider this as the function, this as the solution, and in fact it satisfies, and we find out what is the condition that is required on this m to satisfy this equation 1. So that is what we will be discussing in this session by considering this as the solution. So we proceed with this substituting. So that's the idea why we guess this as the solution and proceed by substituting this. So substituting y equal to e raised to mx in 1 we have. So why we are doing this? Because we are assuming that this is the solution of equation 1, so that is going to satisfy the equation 1, and so we want to know what is the condition that is required on this m. So after substituting this, we know that the double derivative of this, the single derivative of this will be y dash is m into e raised to mx, and so its second derivative will be m square into e raised to mx. So we are going to get m square e raised to mx plus a into m into e raised to mx plus b into e raised to mx is equal to 0. So that is same as writing m square plus a m plus b into e raised to mx is equal to 0, and this gradually implies that, because you know the fact that this e raised to mx will never be equal to 0 no matter for what value of x you give me. So this implies that m square plus am plus b is equal to 0. Okay, I denote this as equation 2, and this is the very important equation to solve the homogeneous linear differential equation, because we determine the value of m through this quadratic equation. So this is called as, equation 2 is called as the characteristic equation of the given differential equation, or it's also called as the auxiliary equation of the given equation 1. And to solve the equation 1, we need to determine the solution of this characteristic equation to determine the value of m. So whatever that value of m will definitely, for that value of m, e raised to mx will definitely satisfy the given equation 1. But our aim, so from here we can get one solution, and you know that this equation will have at most 2 roots. So depending on the roots of this equation, we are going to have the general solution for the equation 1. That is, we have one solution, definitely we have one solution for whatever value of m that satisfies this equation 1. For that value, e raised to mx will always satisfy the equation 1. That is one solution. What about the other solution? So we want two linearly independent solutions to construct the general solution of the equation 1. That is what is very important. So to solve 1 completely, or to find the general solution of 1, to solve 1 is the given differential equation completely, we need two linearly independent solutions. So what I'll do, I'll discuss the cases of this, that again depends on the solutions of this characteristic equation. So what I'll do is that I'll discuss these cases, I'll discuss the 3 different cases for this, because what are those 3 different cases, or what are the 3 different kinds of solution that this auxiliary equation can have. First thing, those 2 roots are distinct, they are real and they are distinct. Second, it can be repeated. Now if this left hand side is a square of any factor, in that case the root is repeating twice. And third case, the roots are complex conjugate. So again, this actually can be categorized into the first case where the roots are distinct, but those are the real roots which are distinct, and in this case we have a complex roots which are distinct. So I would discuss this into 3 cases, and so I would be giving the solution in each case. So case 1, I would be giving the general solution in each case. Case 1, if 2 solutions of this equation 2 are distinct, so if m1, m2 are solutions of 2 such that m1, m2 are real and they are distinct. So again, we need to guess the solution in this case. It's so definitely one root of this equation will be m1, the other root will be m2, and so e raised to m1x and e raised to m2x will always be a solution to the given differential equation. So then y1 is equal to e raised to m1x and y2 is equal to e raised to m2x are the solution of the given equation 1. But what we are looking for, two linearly independent solution. Okay, so we can have one solution. Can this be a can y2 be a linearly independent to y1? So that is the only thing that we need to check. So I mean, I'm claiming here that these are the two linearly independent solution in this case that we will see from the Wronskian of this two function. So are two linearly definitely they are solution. Only thing we need to check whether they are linearly independent or not. Are two linearly independent solutions of 1. S, I'll check the Wronskian of y1 comma y2 at x. Again, this x is coming from the domain of the solution, so that is same as y1 y2, that is e raised to m1 x, and here this is e raised to m2 x. Derivative of this as the second row, that is m1 into e raised to m1 x, and derivative of this here m2 into e raised to m2 x. So this turns out to be you can see that this is same as m2 e raised to m2 x into e raised to m1 x. So e raised to m2 x into e raised to m1 x is e raised to m1 plus m2 x minus this. So here again you will have m1 e raised to m1 x into e raised to m2 x. So that e raised to m1 plus m2 x is the common term, and from that common term what you will remove, from this first term you will remove m2, and from this term you will remove m1. So that is same as m2 minus m1 into e raised to m1 plus m2 x, right? Now this will never be equal to 0. The reason is very simple. We know that this e raised to m1 plus m2 into x will never be equal to 0. So this determinant will be equal to 0 only if m2 is equal to m1 or m2 minus m1 is equal to 0. That is same as saying m2 is equal to m1, which will never happen because m1 is distinct from m2. So this will never be equal to 0 as m1 is not equal to m2, and so the difference will never be equal to 0, and this e raised to m1 plus m2 into x will always be positive. So that's it. So in this case the general solution is given by, in this case the general solution of 1 is given by I'll write down this yg of x is equal to the linear combination of these two solutions, c1 y1 of x plus c2 y2 of x, that is same as c1 e raised to m1 x plus c2 e raised to m2 x. So this I would put in a box because at the end when we want to see the solution of the differential equation we might be using this. So that's it. So this is case 1. We have successfully found the solution for the differential equation when the auxiliary equation have two distinct roots. Now we would discuss one more case wherein case 2. In this case you have, I would take the case wherein the roots are repeating. So how do we write? So if the roots are coincident, that is both the root are same, say I'll call this as m1, this is repeating twice. So basically that auxiliary equation will be of the form m minus m1 the whole square is equal to 0. Now in that case, how do we get the two linearly independent solution? Definitely one solution will be e raised to m1x, and since there is no other root, we cannot directly find the other solution. Okay, so we use the previous lecture technique, that is determining the other solution, because we know one solution, so determining other linearly independent solution from the given solution of the homogeneous differential equation. So one solution over here is y is equal to e raised to m1x. Fine. So to obtain the other solution, we use the formula. We use the formula which we have discussed in the last class to obtain the other linearly independent solution. In fact, that is important, to obtain the other linearly independent solution of 1. What we do is that we take y2 of x as 1 upon, okay, if you remember the formula, it is y1 into something, so that is this is same as y1 of x into integral of 1 upon y1 square into e raised to integral of minus p of x dx. In this case, p of x is equal to a, so not to forget that. So I'll put it over here, y1 of x. A is a constant, so in fact I can directly put the value of that integral y1 square. So here okay, p is your a, so integral of a dx will be same as ax, so this is same as, okay, by the way, what is y1, that also I'll remove. Y1 is e raised to m1x, so squaring it I'll get e raised to 2m1x, and so this will be same as e raised to minus ax into dx. The reason here is your p of x is equal to a. Fine. So this is the integral that we are looking for. But when when we have a repeated root, we can evaluate this a. Basically, okay, I'll call this as star. So basically, how do we obtain the root of this quadratic equation? So the root of this equation roots of m square plus am plus b is equal to 0 are given by this formula, which is that formula m1 is equal to minus a, or in fact in general I'll call this as m is equal to minus a plus or minus root of, okay, in this case my a is equal to 2 and b is equal to a. I hope you know the quadratic formula, so I'm using that. A square minus 4b upon 2 times the coefficient of m square, that is equal to 1, so 2 times 1, so root of a square minus 4b. But since I am saying that m1 is the repeated root of this equation, so in this case we cannot have this plus or minus factor, right? So basically the discriminant in this case have to be equal to 0, because there will be only one value for m which is repeating twice. So therefore a square minus 4b have to be equal to 0, and so that m is equal to minus a by 2, and in this case we are considering m to be equal to m1, so m1 is equal to a by minus a by 2, and from there you can find out the value of a in terms of m. So since m1 is repeated root of m square minus plus am plus b is equal to 0, what we should have is that root of basically that discriminant a square minus 4ab is equal to 0. So a square minus 4b is equal to 0, and so your m1 is same as minus a by 2. This implies that a is equal to in fact minus a is equal to m1. So this you can substitute on the top on star. Substituting this in star, we have okay, y2 of x is equal to y1. Okay, substitute y1 is nothing but e raised to m1x, integral of 1 by e raised to 2m1x, integral of e raised to minus ax. So minus a is 2m1x dx. This gets cancelled, and so we get the solution x, integral of this 1 into dx is x, so x into e raised to m1x. So this is how we obtain the other linearly independent solution. We don't have to check this because we have already treated this as the theorem, and we have proved that y2 given with this formula is the linearly independent to the given solution. And thus the general solution in this case is given by, in this case, that is when the root is repeated, is given by yg is equal to yg of x is equal to c1 y1 of x plus c2 y2 of x, and that is same as c1 e raised to m1x plus, okay, now here the other equation is c2x into e raised to m1x. Remember that m1 is the only root which is repeating twice. So this is again important. I would put this in a box. This is case 2 in a nutshell. Case 3 is when you have two roots which are complex conjugate of each other. So in that case the root will be of this form. I'll write down case 3 if the roots are complex. Say m1 is equal to, okay, now how do we obtain from here, how do we obtain the roots using this formula? And if they are complex, then a square minus 4b have to be negative, right? So the first root is minus a plus root of a square minus 4b upon 2, and m2 is minus a minus root of a square minus 4b by 2. I'll call this as star. In such cases this a1 have to be this discriminant have to be negative. So in such cases a square minus 4b are negative. And so what happens is that when a square minus 4b is negative, inside the root you get a negative sign, which forces to introduce the notation of iota or the imaginary unit. So what I'll do here in this case, I'll call minus c square as this a square minus 4b. Now minus c square is again for my convenience, because so that I mean here this c square is positive, so that this a square minus 4b becomes negative term. C square is always positive for any c in real number, so that I can write down then m1 is equal to minus, okay, if I split the term with the denominator, the first term will become minus a plus 2 and the second term is root of a square minus 4b, which is same as root of minus c square, which is same as root of minus 1 into root of c square, that is c, and so root of minus 1 is iota or I, and it's first m1 is separated by plus, so I into c by 2. So that this is the real part and this is the imaginary part, c by 2, and m2 is minus a by 2 minus I into c by 2. Now since we are discussing the solution on the subset of real number, we expect to have some real solution. Okay, so what I'll do is that I'll form a real solution. In fact, from here you can check that e raised to m1x and e raised to m2x are the solution, and you can very easily check that they are linearly independent solution, but we would obtain a solution from this y1 and y2. So if I take so there's two corresponding solution from here. Corresponding solutions of differential equation 1 are given by y1 e raised to m1 x, that is same as e raised to minus a by 2 plus iota c by 2 into x, and y2 is given by e raised to m2x, which is same as e raised to minus a by 2 minus I c by 2 into x. So now we try to, because this has a complex term, and here I'll be using the fact that we use the Euler formula. I hope everyone knows this Euler's formula, which says that e raised to I x is same as cos x plus I times sin x, and so you can very easily check that e raised to minus I x, this is going to be same as, instead of x you have minus x, so cos of minus x, and being cos is even, I can write down this as cos of x, so sin of minus x will change to minus I sin x. So that is, this is the complex conjugate, e raised to ix is a complex conjugate of e raised to minus ix and vice versa. So I'm going to use this formula. So I construct a solution as per my requirement. What I'll do is that I'll take, because I'm looking for the real solution, I'll be taking a linear combination of these two solutions in such a way that I get the real solution at the end. So the first solution I would be taking from here. In fact, these are also solution. This, as I said, these are the solution to the differential equation, and even you can check that these are the linearly independent solution for the given differential equation. This is actually the generalized case for generalized case 1. Okay, you have two distinct, and so y1 and y2 which are given in this way are the two linearly independent solution. But since we want the real solution, we would get the real solution from this. So consider I'll let y1 star of x, I'll take this as half into y1 plus y2, or you just simply take it as y1 star. It is understood that it is a function of x for our convenience, and y2 star is equal to 1 by 2i into y1 minus y2. Now one thing you can take a note over here, that this y1 star and y2 star are the solution of the given differential equation, because they are simply a linear combinations of to solution of differential equation 1. So therefore I don't have to prove this, we have already discussed this. Both y1 star and y2 star are solutions of equation 1, the differential equation 1. Now I will compute this y1 star and y2 star, and I would show that these are the linearly independent solution. So y1 star here is half time y1 plus y2. y1 is e raised to what? Okay, from here I can directly compute this y1 plus y2 minus a by 2 x plus ic by 2x plus e raised to minus a by 2 minus minus ic by 2x. So from here I can take e raised to minus a by 2 into x common. So I'll write down this as e raised to minus a by 2x, and what remain inside is, from the first term I have e raised to ic x, don't forget that x, and plus from the second term I have e raised to minus ic by 2x. Now using this Euler formula I can write down this whole thing as, okay, instead of x you have now c by 2x. So this is going to be same as, this first term will be same as cos of c by 2x or cx by 2 plus I times sine of cx by 2, and this will be same as cos of cx by 2 minus I times sine of cx by 2. And so you can see that the imaginary term gets cancelled and you have only cos remaining inside, so that will get, so this gets cancelled. And similarly, when you see the subtraction y1 minus y2, in that case you will have 2i sine cx by 2, but that 2i gets cancelled with this 2i, and so you get only the real solution. So this is your y1 star, and so y2 star, similarly you can check this out. y2 star of x will be same as e raised to minus a by 2x into sine of cx by 2. So these are your y1 star and y2 star. Again, to check for the linearly independent, to show y1 star and y2 star are linearly independent. We compute the Wronskian of this y1 star, y2 star at x. This is little bigger determinant, as y1 and y2 has bit complicated term, product of two term, a by 2x, so minus ax by 2 cos of cx by 2, and here I'll write down the second one, y2 minus ax by 2 sine of cx by 2, and so its derivative, you can verify this, this is same as minus half into e raised to minus ax by 2 into a cos cx by 2 plus c sine cx by 2, and here this derivative will be same as minus half e raised to minus ax by 2 a sine cx by 2 minus cos of cx by 2. In fact, this should have been minus c cos of cx by 2. can very easily verify this. Okay, and so this final value of this determinant would be c by 2 e raised to minus ax, which will never be equal to 0 because e raised to minus ax is never 0, 1 by 2 is also never 0. So this will never be equal to 0 provided c is not 0, but you know that c is not 0, because if c is equal to 0, then in that case what will happen? Just look at the case which we are discussing. If c is equal to 0, c is actually the imaginary part, c by 2 is the imaginary part. So if c is equal to 0, m1 and m2 will be a real root, so there won't be difference from case 1, so therefore c is never equal to 0, and that's why this y1 and y2 star are y1 star and y2 star are linearly independent. Now so we have the general solution. Thus in such case, general solution of 1 is given by yg of x is equal to c1 y1 star of x plus c2 y2 star of x, and this would be same as you can in fact check this out. I would take from both the term e raised to minus ax by 2 common, and so what remain inside is the trigonometric term, that is c1 cos of cx by 2 plus c2 sine of cx by 2, right? Now basically this a by 2, if you look at the imaginary and the real part, a minus a by 2 is your real part and c by 2 is the imaginary part, and you know, if this m1 is one root, in this case its conjugate will be the other root, so there will be a difference between the sign, but you just need to know what is the the real and the imaginary part. So here even if you change the sign, that won't make a big difference, I think so. So what you can do now I will write down, I'll give, this is actually in the nutshell, this is how the solution would look like, but to avoid the confusion I would generalize this, that is, if the roots of root of 2, that is auxiliary equation, are complex, say p plus minus iq. P plus iq is complex root and its conjugate, so you can make it out. So if it is of the form p plus or minus iq, then general solution of 1 is given by basically this minus a by 2 in this case was the real root, and plus or minus c by 2 was the imaginary root. So I'll just replace it and write down in the nutshell, yg of x is equal to e raised to, this is px, and c1 cos of imaginary root, that is q, imaginary part, qx, plus c2 sine of qx. So that is the final case, and in this way we have discussed all the cases to obtain the general solution to a homogeneous linear differential equation. And so we would see some illustrative example in the online session for this one. Thank you and have a nice day ahead.